We live in a world captivated by the promise of quantum computing. Headlines scream about its potential to revolutionize industries, from medicine to finance. Quantum computers are touted as the key to unlocking solutions to problems that have stumped scientists for decades. They're painted as the ultimate problem solvers, capable of cracking the most complex codes and simulating the very building blocks of the universe. The technology, still in its infancy, is already attracting billions of dollars in investment. Governments and tech giants alike are pouring resources into the race for quantum supremacy, eager to harness its power. Beneath the surface of excitement and optimism lies a growing sense of unease. Skepticism is brewing within the scientific community, with some experts questioning whether the hype surrounding quantum computing is justified. In this exploration of quantum computing, we'll delve into the heart of this debate. Buckle up because the journey is sure to be filled with twists, turns, and more than a few surprises. Imagine a world where diseases like cancer and Alzheimer's are eradicated, thanks to the power of quantum computers to design life-saving drugs. Picture a future where climate change is tackled head-on, with quantum simulations guiding us towards cleaner, more sustainable energy sources. These are just a glimpse of the utopian vision often painted by proponents of quantum computing. But what about the flip side? The ability to break the world's most sophisticated encryption algorithms could have devastating consequences, potentially crippling global financial systems and jeopardizing national security. The ethical implications of quantum computing are just as profound as its potential benefits. Who will have access to this transformative technology? Will it exacerbate existing inequalities, or could it be harnessed to create a more equitable world? By engaging in open and honest dialogue about the potential benefits and risks, we can work towards harnessing this powerful technology for the greater good.
The road to quantum computing is paved with good intentions, but it's also littered with obstacles. Building a functional quantum computer is a monumental task, fraught with technical challenges that have stumped even the brightest minds. From maintaining the delicate quantum state of qubits to scaling up these systems to a useful size, the hurdles are numerous and complex.
The hype surrounding quantum computing often overshadows the years, if not decades, of research and development still required. While breakthroughs are being made, we are still a long way from seeing quantum computers solving real-world problems on a large scale.
It's crucial to separate the hype from the genuine hope surrounding quantum computing. Progress in this field will likely be incremental, with small victories paving the way for more significant breakthroughs. By embracing a balanced perspective, acknowledging the challenges while remaining optimistic about the future, we can navigate the exciting, albeit complex, world of quantum computing.
All right, folks, let's break down this quantum thing without the fancy jargon. Imagine your computer is like a trusty old car. It runs on bits, which are like the engine cylinders, firing on or off, representing ones and zeros. Every calculation, every email you send, every cat video you watch, boils down to these bits flipping on and off in a specific order.
Now, imagine a supercar sleek and powerful. That's a quantum computer. Instead of bits, it runs on qubits. These are like souped-up cylinders that can be both on and off at the same time.
This mind-bending ability comes from the wacky world of quantum mechanics, where the rules of our everyday reality kind of go out the window. But stick with me, because this is where things get really interesting.
Let's delve a little deeper into the magical powers of qubits. That both on and off thing is called superposition. It's like a qubit is spinning a whole bunch of plates at once, each plate representing a different possibility. And until you stop the spin and take a look, the qubit is holding on to all those possibilities simultaneously.
But wait, there's more. Qubits have another trick up their sleeve called entanglement. Imagine two of those spinning plates miles apart, somehow linked so that when one plate wobbles, the other one does too, instantly.
These two superpowers, superposition and entanglement, are what make quantum computers potentially millions of times faster than traditional computers for certain tasks.
But here's the catch. Harnessing these superpowers is like trying to herd cats. Let's just say building a stable and reliable quantum computer is no walk in the park. So, why bother with these finicky qubits if they're so hard to control? Well, because they hold the key to solving problems that would take classical computers longer than the age of the universe to crack. Think about complex simulations, like modeling the behavior of molecules to design new drugs or optimize financial algorithms.
With their ability to explore multiple possibilities simultaneously, quantum computers could revolutionize fields like medicine, materials science, and artificial intelligence.
Imagine a world where personalized medicine is the norm, where materials are designed with atomic precision, and where artificial intelligence reaches new heights of sophistication.
But before we get too carried away with these futuristic fantasies, let's remember that quantum computing is still in its early stages. It's like the Wild West out there, full of potential, but also plenty of challenges and uncertainties.
Here's the thing about qubits. They're drama queens. The slightest disturbance, a tiny change in temperature, even a stray cosmic ray, can cause them to lose their quantum mojo. This is called decoherence, and it's the bane of every quantum physicist's existence.
Imagine you're trying to balance a beach ball on your nose while riding a unicycle on a tightrope. That's the level of precision required to maintain the quantum state of a qubit.
And because qubits are so sensitive, building a quantum computer is like trying to assemble a watch inside a hurricane.
This makes quantum computers extremely complex and expensive to build and maintain. Think millions of dollars and teams of brilliant minds working around the clock just to keep these finicky machines happy.
The decoherence dilemma, quantum computing's biggest foe. Imagine a concert hall where the slightest cough or rustle of a program causes the entire orchestra to lose their place, descending into a cacophony of noise. That's essentially what happens to a quantum computer during decoherence. Those sensitive little qubits, so full of promise, are easily thrown off their game by the slightest disturbance in their surroundings. Heat, vibration, stray electromagnetic fields, even a stray cosmic ray passing through the wrong atom can cause a qubit to lose its quantum state, collapsing that delicate superposition and turning it into a boring old bit. Scientists are locked in a constant battle to shield qubits from the noisy world, building elaborate isolation chambers and cooling them down to temperatures colder than the depths of outer space. But despite their best efforts, decoherence remains a formidable foe, a constant reminder of the fragility of the quantum world and the immense challenge of harnessing its power. Taming the quantum chaos, the uphill battle of error correction. If decoherence is the villain in the quantum computing saga, then error correction is the valiant hero trying to save the day. Because qubits are so prone to errors, scientists are developing clever techniques to detect and correct those errors before they snowball into a full-blown quantum meltdown.
Think of it like having a team of microscopic mechanics constantly monitoring and repairing your quantum computer, making sure those finicky qubits stay in line.
But here's the rub: error correction in the quantum world is a lot more complicated than hitting the undo button on your keyboard. It requires complex algorithms and a significant overhead of qubits, meaning you need even more of those temperamental particles just to keep the system stable. But if scientists can crack the code of quantum error correction, it could unlock the door to building large-scale, fault-tolerant quantum computers. Scaling the quantum mountain. From qubits to quantum usefulness. Right now, most quantum computers are like those cute little toy cars you see at the amusement park. Fun to ride in for a short while, but not exactly practical for a cross-country road trip. They typically operate with a handful of qubits, maybe a few dozen if you're lucky.
Scaling up quantum computers is like trying to build a skyscraper out of Legos. It's not just about stacking more blocks on top, it's about creating a stable and interconnected structure that can withstand the weight of its own complexity.
As the number of qubits increases, so does the difficulty of maintaining coherence and controlling errors. So, while we marvel at the potential of a few dozen qubits, remember that we're still at the base camp of Mount Quantum, with a long and arduous climb ahead before we reach the summit of true quantum usefulness.
The quantum price tag, a technology for the elite? Let's face it, quantum computing is not exactly a budget-friendly endeavor. Building and maintaining these complex machines requires deep pockets. Think billions of dollars deep.
From the specialized equipment and cryogenic cooling systems to the army of brilliant minds needed to operate them, the cost of entry into the quantum game is astronomically high.
Right now, only a handful of governments and tech giants like Google, IBM, and Microsoft have the resources to play in the quantum sandbox. This raises concerns about accessibility and the potential for a quantum divide, where only the wealthy and powerful can harness the benefits of this transformative technology.
Imagine a world where life-saving medical breakthroughs are out of reach for developing nations, or where the ability to model climate change solutions is limited to a select few. Ensuring equitable access and responsible development will be paramount to harnessing quantum computing for the benefit of all humankind.
The skeptics emerge, whispers of doubt in the quantum wind. For all the excitement surrounding quantum computing, a growing chorus of skeptics is starting to make itself heard. These voices, often drowned out by the siren song of quantum hype, are raising important questions about the feasibility, practicality, and even the ethical implications of this rapidly developing technology.
While acknowledging the potential of quantum computers, these skeptics caution against overblown expectations and the tendency to view quantum computing as a panacea for all of humanity's problems. They point to the numerous technical hurdles, the slow pace of progress, and the limited applicability of quantum solutions to everyday challenges.
The debate within the scientific community itself is heating up, with some researchers expressing cautious optimism while others remain deeply skeptical. By separating the genuine promise from the inflated expectations, we can gain a more realistic understanding of this complex and evolving field.
Beyond the hype, tempering expectations, embracing reality. The trajectory of many emerging technologies follows a familiar pattern. Initial excitement leads to inflated expectations, followed by a period of disillusionment as the limitations become apparent, and eventually, a more realistic assessment of the technology's true potential emerges.
While the potential benefits of quantum computing are undoubtedly significant, it's essential to remember that this technology is still in its early stages of development. Comparing it to the early days of classical computing, we are still decades away from realizing its full potential.
Instead of expecting quantum computers to revolutionize everything overnight, we should focus on identifying specific areas where they can make a tangible difference. By tempering our expectations and focusing on achievable goals, we can avoid the pitfalls of hype and ensure that quantum computing develops into a technology that benefits society as a whole.
One of the most frequently used and often misunderstood terms in the quantum computing lexicon is quantum supremacy. This buzzword, often touted as a milestone in the field, refers to the point at which a quantum computer can outperform the best classical computers on a specific task.
However, the concept of quantum supremacy is often misconstrued. Achieving supremacy on a carefully chosen, contrived task does not necessarily translate into practical advantage or real-world usefulness. It's like claiming victory in a race where you got to choose the terrain and the rules.
Moreover, the bar for classical computing keeps getting higher. As classical algorithms and hardware improve, so too does the challenge for quantum computers to demonstrate a clear advantage. It's a constantly moving target, making it difficult to definitively declare quantum supremacy.
Instead of getting caught up in the hype surrounding quantum supremacy, we should focus on developing quantum algorithms that offer a clear and demonstrable advantage over classical approaches for real-world problems.
It's becoming increasingly clear that quantum computing is not a one-size-fits-all solution. Instead of replacing classical computers entirely, quantum computers are more likely to complement them, offering a specialized toolset for tackling specific types of problems.
Just as you wouldn't use a sledgehammer to crack a nut, you wouldn't use a quantum computer to send an email or edit a document. Classical computers excel at everyday tasks, while quantum computers shine when it comes to complex simulations, optimization problems, and breaking certain types of encryption.
By focusing on these niche applications, we can leverage the unique capabilities of quantum computers to make meaningful progress in areas such as drug discovery, materials design, financial modeling, and artificial intelligence.
Rather than viewing quantum computing as a silver bullet, we should embrace its role as a specialized tool within a broader computational ecosystem. By identifying the right problems for quantum computers to solve, we can unlock their true potential and drive innovation in a wide range of fields.
As the quantum computing race heats up, a sobering question emerges. Will this revolutionary technology widen the gap between the haves and the have-nots? Quantum computing risks becoming the domain of a select few, powerful corporations and wealthy nations.
This potential disparity raises concerns about a quantum divide, mirroring the existing digital divide. The implications for global equity and social justice are profound.
Bridging this emerging divide requires proactive measures to ensure equitable access to quantum technology. This includes fostering international collaborations and promoting open-source development.
Failure to act decisively could exacerbate existing inequalities, creating a world where the benefits of quantum computing are enjoyed by a privileged few. Encryption under siege, the security threat of quantum codebreaking.
Our digital world relies on encryption to protect sensitive information, yet quantum computers pose a formidable threat. Shor's algorithm can theoretically crack encryption codes. This could lead to digital chaos.
Imagine hackers with quantum computers breaching bank security. They could hold sensitive data hostage. The ramifications are staggering.
Fortunately, the threat is not immediate. Quantum computers powerful enough to break encryption are still years away. But proactive measures are needed to safeguard our digital future.
Section 3. Quantum Ethics, Navigating Uncharted Territory.
The rapid advancement of quantum computing presents unprecedented opportunities and ethical dilemmas. As we delve deeper, we enter uncharted territory, raising questions about responsibility and potential for both good and harm.
One pressing concern is bias in quantum algorithms. Ensuring fairness and mitigating bias is crucial to promote equitable outcomes.
Another consideration is the impact on the workforce. Quantum technology could create new industries and employment opportunities.
Addressing these ethical challenges can harness quantum computing for a just and equitable future.
The future of quantum computing should not be dictated by a select few.
Unlocking its potential requires a global effort, embracing open access and collaboration.
Just as the internet democratized information, we must democratize quantum computing.
Open source development is crucial in this endeavor.
Making quantum tools freely available empowers global innovation.
International collaboration is vital for progress. So, after this deep dive into the world of quantum computing, where do we stand? Is it the revolutionary force it's often portrayed to be, or is it destined to remain a scientific curiosity? The answer is nuanced and complex. We've explored the immense potential of quantum computers to revolutionize fields like medicine and artificial intelligence, offering glimpses into a future where challenges become solvable. Yet, we've also encountered formidable hurdles like decoherence, error correction, and cost. The path forward requires a delicate balancing act, embracing potential while acknowledging limitations. Instead of a sudden revolution, the quantum future will unfold gradually, with incremental advancements paving the way for breakthroughs.
Think of it as a slow climb up a mountain, each step bringing us closer to the summit.
Quantum computers will make inroads into fields like materials, science, drug discovery, and financial modeling.
These niche applications will refine the technology for broader adoption.
The true power of quantum computing may lie decades from now, with large-scale, fault-tolerant machines. The journey into the quantum realm is not one we undertake alone. It's a shared endeavor, requiring collaboration, open dialogue, and a willingness to embrace uncertainty.
Scientists, engineers, ethicists, policymakers, and the public all have a role to play in shaping this transformative technology for the betterment of humanity.
Investing in quantum education and research is crucial.
Nurturing the next generation of quantum pioneers, equipping them with the knowledge and skills to navigate this complex landscape, is an investment in our collective future.
Equally important is fostering open access to quantum technologies, ensuring that the benefits of this revolution are shared broadly, not confined to a select few.
Open source software, shared infrastructure, and international collaborations are essential to democratize quantum computing and unlock its full potential for good.
The quantum future is not predetermined, it's a future we create together.
By embracing a spirit of collaboration, curiosity, and ethical responsibility, we can navigate the challenges and opportunities of quantum computing, steering this transformative technology towards a brighter future for all.